So how would you interpret this period?
For 1 second, for every 1 second, you can see 4 cycles.
That's true. But what would be another way to interpret this?
There's 1 cycle per 1/4 of a second.
Okay, right. It takes a 1/4 second to go through 1 cycle. It takes a 1/4 second to go through 1 cycle. Okay. And how would you interpret this number?
4 cycles over 1 second.
What does that mean in words again?
That means for every 1/4 of a second, there's.
Well, let's actually interpret it in terms of these numbers over here.
There's 1 cycle for every 4th second.
Oh, you're still looking at this number down here. How would we interpret this frequency? Just in terms of these numbers right
There's
here.
4 cycles per second.
Yeah, or in 1 second, 4 cycles will pass. In 1 second, 4 cycles will pass. Do you see how these are two sides of the same coin? How long does it take to go through 1 cycle?
1/4 of a second.
So we can pack 4 of those babies into 1 complete second, right? If it takes a 1/4 second for each cycle, then we can fit 4 complete cycles in the whole second over here. So it should be clear that the frequency and the period are reciprocals of each other. They kind of are two ways of giving the same information. Okay. All right. By the way, the frequency and the period you're going to use on and off throughout the whole rest of the course and next semester too. So it's really important not to lose sight of these units. Anytime you're working with these, you have to ask what are the units, and that reminds you what the difference is between frequency and period. All right, now let's say that the period is big. For example, let's say that the period is, say, 1 million seconds per cycle. Does that mean the wave is oscillating fast or slow?
Slow.
Yeah, how do you know? How would you interpret this?
It takes 1 million seconds for 1 cycle to.
Yeah, well, that seems like a lot of seconds, right, for just 1 cycle. If it takes 1 million seconds to go through 1 cycle, it must be going very slowly down. If it's going to take 1 million seconds before my hand gets back up to the top again, that would be a really long time. So t is kind of a measure of how slow the wave is going. T is a measure of the slowness of the wave. That makes sense because t stands for time. Well, when do things take a lot of time? When you're slow. Things take a long time when you're slow. So if you have a long period, that means it takes a long time to go through a cycle. Well, that's because you're a slowpoke. All right. Now suppose that f was big. Suppose that f is 1 million hertz. Well, how would we interpret that 1 million hertz?
There's 1 million cycles per 1 second, so it's going very fast.
Yeah, in 1 second, it's going through 1 million cycles. Wow, there's no way I could even approximate that with my hand, right? I could do maybe at best, maybe 2 cycles per second. No way 1 million cycles per second. Okay, so I think you already figured out the frequency measures how fast the oscillations are. Frequency is a measure of fastness. A big frequency means that you're oscillating quickly. Okay. It's not too hard to remember. Kind of as a memory aid, we could imagine that F stands for fastness. I don't know if that's really a word. But anyway, F would stand for fastness here. And then this has to be slowness. Again, this is the time. Well, when you're slow, things take a long time. Very often people get these two things reversed, and they forget which one is measuring the slowness and which one's measuring the fastness. Now, neither of those sound like words. So if the frequency is big, would the period be big or small?
If the frequency is big, the period is small.
First of all, we know that because they're measuring opposite things. But we can also see that from the equation, right? Because they're reciprocals of each other. So if this is a small number in the denominator, that would make a big fraction. Or if this is a big number in the denominator, that would make a small fraction. So when things are reciprocals of each other, they have to move inversely with each other. So again, when f is big, t is getting small. When t is small, f is getting big. They move inversely. After all, remember here we had a frequency of 1,000,000 hertz. So what's the period?
1 cycle, I'm sorry, 1 over 1,000,000
And the units are?
seconds
What would be some better, easier to interpret units?
per cycle, per 1,000,000 cycle.
So how would we interpret this?
It takes 1 second per 1,000,000 cycles.
That's true, although that's really the same as we had over here.
Yeah.
Remember, we like to put a 1 on the bottom. It's easier to interpret a concept if we put a 1 on the bottom.
So where would the 1 go in front of the cycle? Oh, okay, so the reciprocal would reverse, it would be 1,000,000 seconds per 1 cycle.
How would we interpret this? We interpret it that to do 1 cycle takes 1,000,000th of a second.
Okay.
To do 1 cycle takes 1,000,000th of a second. Is that a long time or a short time?
It's a short time.
Right. Well, again, so these shows these two are reciprocals of each other. We knew this frequency is very big. That means that we were oscillating very quickly. Well, then the period should be very small. These move inversely to each other. When the frequency is very big, 1,000,000, the period will be very small, 1,000,000th. When the frequency is big, its reciprocal is small. So when the frequency is big, its reciprocal should be a very small number. Okay. So if the frequency is 3/4 hertz, how will we find the period?
So it's 1/3 second for 1 cycle, right?
Right. To do 1 cycle takes 4/3 of a second. Sometimes it would be best to turn this into a decimal. How would you turn this into a decimal? Not quite sure how to turn 4/3 into a decimal?
No.
Well, you know this means divide, right? This means 4 divided by 3. That's how you turn it into a decimal. You would do 4 divided by 3. That's what you would probably have to do on the test, so I guess we should be practicing that.
1.3.
So what's the period?
1.3 seconds for every 1 second.
Yeah, actually, usually in a course like this, you're going to be putting things into decimals. All right, well, the way you change a fraction into a decimal is by doing the division, 4 divided by 3. Okay. All right, well, now we're going to go on to our next concept. So again, we can put in the little arrow here. And the next concept is what's called the angular frequency. Now, we already saw something very similar to the angular frequency when we talked about the angular speed. The angular frequency and the angular velocity really behave the same. Do you remember what the symbol that we used for angular velocity?
Angular velocity was alpha. Oh, that's acceleration. Angular velocity was omega.
There you go. Good. Well, it turns out that angular frequency and angular velocity are very similar concepts. Pretty much everything that's true for one is true for the other. So we're going to keep using omega here. Well, then we should remember what are the units for omega. Remember, that was the angular velocity.
It was radians per second.
Radians per second. Good. That's not too hard to remember because it's an angle measure. Well, angles are measured in radians. All right, now over here we were talking about cycles, and here we're talking about radians. What's the relationship between those? Do you remember how many radians are there in a cycle? Have we talked about that? Do you know how many radians there are in a cycle? Do you know how many degrees there are in a cycle?
Isn't it, well, in a complete,
So a cycle would be like a circle, I should explain. We can represent a cycle as a circle, so
it's 2 pi.
there, that's right. A cycle is like a circle. Well, there's 2 pi radians in a circle or a cycle. We could say 360 degrees, but we're not really, this is not a part of physics where we use degrees, we use radians. So there's 2 pi radians in a cycle.